John Michell. In 1783, a quiet English clergyman sat down and wrote a letter that should have broken science. He calculated that a star massive enough could trap its own light. Not dim it, trap it completely. He called them dark stars. The idea was so far ahead of its time that almost nobody took it seriously. Michell's math was sound, but the physics of light wasn't fully understood yet, and the concept floated in academic limbo for over a century. The man who first described a black hole died in 1793 without ever knowing what he had started. Pierre-Simon Laplace. A decade after Michel, this French mathematician independently arrived at the same terrifying conclusion. A star with enough mass would create gravity so strong that escape velocity would exceed the speed of light. Laplace published the idea twice, in 1796 and 1799. Then he quietly removed it from later editions of his own book. Why? Because new wave theories of light suggested light couldn't be captured by gravity at all. Laplace buried one of the most important ideas in the history of physics to protect his own reputation. The concept vanished from mainstream science for over 100 years. Albert Einstein. In November 1915, Einstein published the field equations of general relativity and changed everything. He showed that mass warps space-time itself. Gravity isn't a force pulling objects together, it's a curve in the fabric of reality. Einstein thought the equations were too elegant to be wrong, but he also believed they would never describe anything real at extreme scales. He was wrong about that second part. Within weeks, someone else took his equations further than he was willing to go. Carl Schwarzschild. He was doing artillery calculations on the Russian front in 1915 when he solved Einstein's equations exactly. From a World War I trench, Schwarzschild derived the precise geometry around a perfectly spherical mass. His solution revealed something disturbing at a critical radius, now, called the Schwarzschild Radius, space-time curves so severely that nothing escapes. Not matter, not light, not information. He mailed the solution to Einstein from the front lines. Einstein called it a splendid result. Schwarzschild died of disease at the front just months later, never knowing his name would define the edge of the universe's most extreme objects. Subrahmanyan Chandrasekhar. In 1930, a 19-year-old Indian physicist boarded a ship to England and spent the voyage doing calculations that terrified the establishment. He proved that stars above a certain mass, roughly 1.4 times the mass of the Sun, cannot stabilize as white dwarfs when they die. They must collapse further, possibly without limit. When he presented this to the Royal Astronomical Society in 1935, the legendary Arthur Eddington publicly mocked him, called the idea absurd. Chandrasekhar was humiliated and sidelined for years. He eventually won the Nobel Prize in 1983. Eddington had spent decades defending a universe that didn't exist. Robert Oppenheimer. In 1939, the physicist who would later build the atomic bomb co-authored a paper with Hartland Snyder that crossed a line most scientists refused to approach. Oppenheimer showed mathematically that a massive enough collapsing star would not stop. It would compress into a point of infinite density. A singularity. The paper was published on September 1, 1939, the same day Germany invaded Poland. It was almost completely ignored. World War II swallowed the physics community whole, and the idea of stellar collapse into infinite density sat on the shelf for 20 years. John Wheeler. By the late 1950s, the concept still had no name. Scientists talked around it in awkward clinical language. Wheeler changed that in 1967 when he coined the term black hole during a lecture in New York. The name was almost too good. It spread instantly. It gave the public a handle on something genuinely incomprehensible. Wheeler spent decades pushing physicists to take the idea seriously, but the name did something unexpected. It made the concept feel like science fiction, which gave serious researchers an excuse to keep their distance. The word that made black holes famous also made them easier to dismiss: Cygnus X-1. The first serious candidate for a real black hole wasn't found by a telescope pointed at the sky. It was found by a rocket carrying detectors above Earth's atmosphere in 1964. The source was a powerful X-ray emitter in the constellation Cygnus. By 1971, astronomers traced it to a binary system where a visible star was being stripped of material by an invisible companion. That companion was too massive to be a neutron star. Stephen Hawking famously bet Kip Thorne in 1974 that Cygnus X-1 was not a black hole. Hawking lost the bet in 1990 and paid up with a subscription to a magazine. The first confirmed black hole was won in a wager, Stephen Hawking. In 1974, Hawking published a result that stunned everyone, including himself. Black holes aren't entirely black. They emit radiation. Quantum mechanics near the event horizon causes particle pairs to spontaneously appear. One falls in, one escapes. Over vast timescales, a black hole slowly evaporates. This meant black holes had a temperature. It meant they could eventually die. It also created a crisis called the information paradox. If a black hole evaporates completely, what happens to all the information about what fell in? Physics says information cannot be destroyed. Hawking radiation suggested it could be. That contradiction is still not fully resolved today. Andrea Ghez and Reinhard Genzel. For decades, the center of our own galaxy was a mystery wrapped in dust. In the 1990s, two independent teams, one led by Ghez at UCLA and one by Genzel in Germany, began tracking individual stars near the galactic center using infrared telescopes. What they found was extraordinary. Stars were orbiting an invisible point at speeds that made no sense, unless something with 4 million times the mass of the Sun sat at the center. They had mapped the gravitational signature of a supermassive black hole called Sagittarius A star. Both researchers shared the Nobel Prize in 2020. The black hole at the heart of our galaxy had been hiding in plain sight, the Event Horizon Telescope. On April 10, 2019, a press conference went live simultaneously in 6 cities. The image that appeared was blurry and orange and shaped like a ring of fire. It was the first direct image of a black hole's shadow, specifically the supermassive black hole at the center of galaxy M87, 55 million light-years away. The Event Horizon Telescope wasn't one telescope. It was 8 radio observatories across 4 continents, operating as a single Earth-sized dish. The data required half a ton of hard drives to transport. The algorithm that processed the image was co-developed by a young researcher named Katie Booman, whose photo went viral the moment the image dropped. A century after Schwarzschild's equations, humanity had finally seen one: gravitational waves. On September 14, 2015, at 5:51 in the morning Eastern Time, 2 detectors in the LIGO experiment registered a signal lasting less than a second. It was a ripple in spacetime itself. 2 black holes, roughly 29 and 36 times the mass of the Sun, had spiraled together and merged 1.3 billion light-years away. The collision released more energy in that fraction of a second than all the stars in the observable universe combined. The signal matched Einstein's predictions almost perfectly. LIGO's founders won the Nobel Prize in 2017. The universe had been broadcasting these collisions for billions of years. Humanity had only just built ears sensitive enough to hear them.